So good afternoon, everyone. I'm really pleased to be here this afternoon, even if it's not, if we are not together. I am in Quebec, in Sherbrooke, in Canada. So just like the two previous presenters, Mohamed and Montessier, I'm in Canada too. I will present today on behalf of two of my former master students, Mrs. Melissa Barrière and Mr. François Dalin, who are now engineers in Quebec too, and also on behalf of my co-supervisor, Professor Jean Proulx. And the project is on the influence of two different simplified cell structure interaction models on the seismic response of a highway bridge. It's a case study project that we are presenting. So actually, this project started a few years ago, and it started with the study of three different bridges, typical highway bridges in Quebec. But today I will really focus on one case study, one bridge, the Chemin Roi. I don't know why I chose this one, because of the name maybe, but maybe because it's in Magog where I live, I don't know. It's a typical highway bridge, actually. And we will so focus on this, and I will present some conclusions from previous work, numerical modeling details with OPENSEES, some results and conclusions. So in this project, at first we did a dynamic in situ test campaign under ambient vibration and force vibration on three bridges. It allowed us to calibrate the numerical models. And in the first part of the project, we calibrated the models on a rigid foundation. And then in this second phase of the project, we compared the superstructure displacement and base shears obtained with this rigid foundation model to two simplified methods. The first one proposed in the 2014 edition of the Canadian Highway Bridge Design Code, which is a simplified method. Like Mohamed presented different method, this is a simplified method on without damping. And then we compared it with the method from the US National Earthquake Hazards Reduction Program, the NEHRP 2012, which is quite similar but includes damping in the model. So just for comparison purpose. Actually, we know here in Quebec, at least, which is a low to moderate seismic zone region, that in practice, the engineers will model on rigid foundations. So we wanted, the purpose of this project was to compare what is it worth to model some simplified substructure model, and what is the impact of that on the superstructure and on the base shear of the bridge bed. And what is two simplified linear models, one with and one without damping. So this is the bridge located, like I said, in Quebec, in Magog, right here on Highway 10, and the University of Sherbrooke is somewhere here, and my house is right there. So it was really convenient to test this bridge. It was built in 2009. It is approximately 194 feet long and 37 feet wide. So really typical, with almost a very low skew of 6 degrees. It is a concrete deck resting on 4 steel beams. It's on a shallow foundation, and the foundation type is of type C in the CHBDC, Canadian Highway Bridge Design Code, which is a very dense sort to soft rock. The multi-layered elastomeric bearings of the south abutment here, and the unidirectional confined bearings here on the bridge vent are fixed in both longitudinal and transverse direction. And the movements are restrained on the transverse direction, but allowed in the longitudinal directions for the north abutment. The information, like I said, the information we collected during the in-situ dynamic tests allowed for the calibration of the 3D numerical model for the bridge. The results from ambient vibration tests Well, it's easier. It's fast. It's quick to complete. It allows for many stations, recording stations. However, like what you see on the right, the force vibration test with a small shaker were performed afterwards. It takes more time, but it is really more precise. You get better definition of the response curves, and then hence you will have better frequencies, mode shapes, and damping results. But you do have to close the bridge. That's why you see it's pretty dark. We have to do this at night. So for the 3 bridges that we tested, we did the ambient vibration test during the day, and then we closed the bridge, and at night we did the force vibration test. So on this table, you see some results of the different mode that we obtained from the force vibration test. You can also see the model assurance criterion here. It shows that there is a good correlation with the numerical models that we calibrated. These data are also used for the selection of the synthetic accelerograms that we will use for the analysis, and also for the definition of the dimensionless frequency value required in the NEHRP methodology. Finite element models were developed using OPENSEES, just like my previous colleagues. I will present some of the modeling details that we use for the superstructure, and afterwards I will talk a little bit about the 2 SSI model we use, and also a few words about the input ground motion that we selected. So the superstructure was modeled using a grid of nodes that were connected by linear elements of the elastic beam column element type. So it allows for a realistic distribution of the rigidity of the beam and diaphragm that are combined with the slab. The nodes were positioned vertically at the central end of the composite elements formed by the beams, the asphalt, and the slab. So it implies that the masses of all these elements are included in the model. Here you have the bridge band. In this model, so it's a typical bridge. Most of the dissipation, energy dissipation, will take place in the columns, in the plastic zone region at the top and the bottom of the columns. We use the concrete 06 model for the concrete and steel for the reinforcement. So it's quite typical models, really. For the elastomeric bearings, we use the zero length element to connect the 2 nodes located at the same location. Here we consider no deformation under gravity loads. We use the steel zero material to simulate the historical damping of this material. And also linear behavior is assumed for the 3 degrees of freedom in the rotation. Like I said previously, short and medium span bridge, at least in Quebec, which is a low to moderate seismic region, we often model by considering only a rigid foundation. But in this project, we decided to compare this response to 2 models with considering a SSI model. The first one is the Canadian Highway Bridge Design Code, the S6-14 methodology, in which the footing is modeled as a rigid element. It's a spring model distribution, a really simple spring model distribution. It is linear. And also the NEHRP methodology, which considers also damping and is also a linear model. So really 2 simplified models. For the abutment, the stiffness of the backfill and the abutment wall is represented with an elastoplastic material with a gap, and transversal response. The contribution of the transverse stiffness was not considered as is recommended in Caltron and other guidelines. So here you can see that the soil type that we considered in this project, well, the bridge is on type C, but we also modeled it on type D just for comparison purposes. Okay, so those are the categories of soil type in Canada. We use the synthetic accelerograms according to the National Building Code of Canada 2015, which were presented by Professor Atkinson and Al. The response spectra resulting from the accelerograms were calibrated on the target spectrum for a given range of periods, so really short periods. You see here the first frequency of the bridge was quite short, and I put a red circle here around the area of interest. What you can see is the mean spectrum varies a little bit around the target spectra, so it gives some different results. If you shift your period with the SSI model and you're in a region where you're in an upward slope, like it is in this case, you will get higher demand on this region with the SSI model, which might not be what we would expect. But in this case, really, this is what happened. So you get the results now. And I think I'm still on time because I'm on the results already. So what you get here is the displacement response in the longitudinal direction and the transverse direction, and we compare the rigid model, the simplified model in the CHBDC S6-14, and in the NEHRP guide. I have the results here in millimeter. I gave you just an idea what it means in inch of so if some of you are not familiar with the metric system, you can have an idea. So what we see is the results from the maximum displacement response from 11, computed from 11 time history analysis. And the results show that in the SSI methodology will give higher results when you compare it to a model without damping. But when you add damping, it is interesting to see that you come back closer to the model on a rigid foundation, which is kind of normal. You're adding damping, so it's a bit less severe, I would say. But I would like to note that even though like 148% might look like a lot, you are still in the range of 3 millimeters. So it's not that much, okay? I would like to remind that it's a low to moderate seismic zone. So in this case, you have the shear response at the base of the bridge vent in the longitudinal and transverse direction. Again, the results here are in kilonewton, but I gave you an idea of what it means in pounds. So like I said, the natural periods typically short for this type of bridge due to its relatively high stiffness. And the period will increase when the foundation model are introduced. But for this bridge, particularly, the measured vibration periods are located along an upward slope of the mean spectrum. So this is why we see an increase in the shear response when we add the model, the SSI model. But again, when you consider damping, it goes down. So the conclusion, we presented the case study, numerical investigation of the effect of two different simplified soil structure interaction models with and without damping. And on a model that was calibrated using ambient and force vibration tests on a real bridge. We have to notice that it is in an area of low seismicity. So the overall impact, I must say, of including the SSI models did not result in much larger displacement of its shears. But however, given the relatively I would say, low amount of additional effort for this type of bridge to include a model, including the spring and the damper system. We would recommend to use a model including damping and condition flexibility and energy dissipation. And this is a message from my two former students who are working in bridges right now. They said that it's worth it to include those simplified models, but be careful if you use what is in the code right now without the damping. It's a bit different. You get different results. So if you do it, just go ahead and include the damping too. It's not that much more effort to include the damping too. So that's it.
Thank you very much, Nathalie. Thanks. Thank you for the presentation.